All right, everybody. Hello. Today I'm going to be talking about the geometric series. So, the geometric series is an infinite sum. Let's write that. So, the way the geometric series works, and you'll see where this term geometric fits in later. But the way this works is you start with a number. Typically you start with 1. And then you reduce, you divide it or multiply it by a ratio. So in our case, let's pick our ratio to be a fourth. We're going to multiply it by a fourth to get the next term, and then we do that again, and again, and again, and again. And you do that forever, and that is the geometric series. But of course, if it goes on forever, how are we ever going to get a number out of it, right? You can't calculate infinitely many terms. You have to stop somewhere. So let's stop here. Stop after the third term, which is, technically speaking, before we go on, this is the second term because of the power is the second power. This is the first power, and you might be wondering why we start with a 1. This is 1 over 4 to the 0th power. So this is typically called the 0th term. Okay, so let's take 3 terms, or let's stop at the second term, and let's calculate a partial sum. Let's see what that is. Well, let's give them a common denominator. We'll do 16 because of 4 squared. And this is 1.3125. Exactly, or about 1.3. And you can keep adding terms. And you can add as many terms as you want. And I guarantee you can add as many terms as you want, but you'll never get to 4/3. You'll never equal 4/3, and you'll never get greater than 4/3. You can add as many terms as you want, and in fact you can get as close as you want to 4/3. You can get arbitrarily close to 4/3, but you'll never get to 4/3. And I would say calculate it for yourself to prove it to yourself, but I've got here a big list of numbers. You can kind of ignore this prelude and this little line of programming here. What's to note is that you start at 1, you add a fourth, so that's 1 plus a fourth. There's our number here. 1 plus a fourth squared. And you can keep adding terms. You can see you get so close to 1.3, 4/3, 1.333333333. 4/3 is 1.3333, 3 repeating. Right, and you can see even at some point the difference gets so small when you add more and more terms that it's not even registering here. But the point is that in the real world you can never get to 4/3. But you can get as close as you want. But mathematically we can show, even if in the real world we can't show this, mathematically we can show that if you have infinitely many terms, series is exactly 4/3. Okay, it's exactly equal to 4/3. And we can use tools, mathematical tools, to show that that's true. The way we're going to do that first is we're going to show a geometric proof. I'm going to prove it to you geometrically. There's a really cool way to show that this infinite sum, this geometric series, is equal to 4/3. And this is where the geometric part of the name comes from. And if it isn't, then I don't know where else it could come from. There's a bunch of ways to do this. The way I'm going to do it is we're going to do the 1/4 ratio. Looks like a V. Ratio case. This is the same series we've got right here, where 1/4 kind of defines our geometric series. What we're going to do is we're going to draw a square, and this is a unit square. In other words, the sides are 1 and the area is 1. Then what we do is to introduce the ratio is we divide our square by area into quarters. Okay, side length of a half. Half times a half is a fourth. There's our quarter. Of course, we have 3 other quarters. So here's the other 3. Here's 1, 2, and 3. So what we do next, and some of you might be guessing this, is we pick a different quadrant and we do the same thing over again. We take a quarter and we turn it into quarters. We take a fourth of the square and we divide it into fourths. Again, so that would be our 1 is our square, a fourth is a fourth of the square. A fourth squared would be a fourth of a fourth of a fourth. Now you can pick any one of these 3, but we're going to pick this one in the top right. And you might be wondering, well, why are we doing that? And the best answer I can give you is that it makes it obvious what's happening, and you'll see what I mean. So just trust me that you want to choose this one in the top right. Okay, so what we're going to do is we're going to take this quarter and split it into quarters. Here's our quarter squared. And then we're going to do the same thing. Right, here's our quarter of a quarter, and here's our quarter of a quarter of a quarter. Here's our 1/4 cubed. Do the same thing. You guessed it. Here's our 1/4 squared. Keep on going. 1/4 to the 5th power. This is our 1/4 to the 4th power. I think I said squared there. 1/4 to the 5th powered. 1/4 to the 6th power. So on. You do this forever. And you can see that there's a kind of a telescoping series of squares that are getting smaller and smaller and smaller. The area is being reduced by a fourth. And even better is that you get the same series of squares here. And you get the same series down here. Now, isn't that cool? And if you take infinitely many divisions, you can see that you get 3 copies of the same series. And if you take infinitely many divisions, the whole original unit square is filled up by area. And with 3 different copies, that means 1 copy which is a fourth, plus 1 fourth squared, that's 1 over 4 cubed, plus off to infinity is equal to a third. But original series had a 1 in front. You can think of that as, you know, the original square. So 1 plus fourth plus 4 squared plus yada 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 is 1 plus a third, which is 4 thirds. So isn't that cool? We showed geometrically that this infinite sum, this geometric series, is equal to 4 thirds. I think that's pretty cool. And some people do this with a triangle. You can do this with a triangle. I don't have much room, but the way you do it is you divide the triangle into 4 bits. The way you do that is, looks a little bit like the Triforce. 1, 2, 3, 4 triangles. And you can do this with other ratios too. You can use a half, and I invite you guys to try a half. It's not as cool as this one. It's not as interesting. The pattern is not as cool. But it turns out when you do it, you only get one kind of series, and it fills up the whole square. So you know, a half plus a fourth plus an eighth plus a 16th plus a 32th plus yada 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 is equal to 1, which is pretty cool, and it's alright. But we're not going to be proving geometric series and infinite sums geometrically forever, so there is an algebraic way. And this is typically what you'll be seeing if you work with geometric series or infinite sums, so do it algebraically. So what we're going to do is use the same sum, the same series, and we're going to call it S. S for series, or sum. So 1 plus a fourth, plus 4 squared, plus a fourth cubed, plus yada yada yada. And again, the ratio that defines our geometric series is a fourth. And you can see that as sort of, for a visual learner, that is taking your square or your triangle or whatever shape you want to use and splitting it into that many pieces and doing that recursively forever until you get something. So what we do now is take note of two things. We're going to kind of leverage two facts to get an answer for S. The first fact, and let's choose a nice different color, facts. Fact number 1 is that the terms in this series are related in a very simple way. You can find out what the next term is with something called a recursion relation, or even, you know, the term before it. And in fact, you can kind of build the whole series with just this recursion relation. And that is that this, let's call the nth term in this series Sn, S sub n. In other words, you know, S0 is equal to 1. S1 is equal to a fourth, right? Because we get the next term in this series by multiplying the previous one by a fourth. S80 is 1 over 4 to the 80th power, because we've multiplied S0 by a fourth 80 times. And you know, that's another handy reason why we start with 0. We zero index. And you know, also remember the 0th term is 1 over 4 to the 0. It's not 1 over 40, that's 1 over 4 to the 0. So the nth term is Sn, and this recursion relation is Sn minus 1. So you take the term before it and you multiply it by a fourth. Like I said, this is sometimes called a recursion relationship. Okay, so that's the first thing, is that there's a way to build the whole series using just one equation and you can find out if I plop you at any point in the series, you can find out what the next term is or what the previous term is, or you could even start from there and build the whole series. And the second thing is that S is infinite. Now, this might not seem like an advantage right now, but some of you might be getting ideas already. The idea is that we're going to abuse infinity. Huge air quotes there. Take that with a grain of salt because, well, hopefully you'll understand what I mean in just a second. So what we're going to do is we're going to rewrite S. I'm just going to write a few terms here. Don't need many. So to start, and some of you might be thinking, sorry, what this recursion relationship is really simple, and you might wonder, well, what happens if we just multiply S by a fourth? What if we multiply everything in S by 1/4? What would happen? Because the only thing that defines S is 1/4. If we multiply a term by a fourth, we just get another term in S. So we're basically taking every term in S and turning it into a different term in S. So let's go ahead and do that. So 1 becomes a fourth, 4 squared, so on. Here's where we use fact number 2. So fact number 2, since it's infinite, a quarter S has all of the same terms as S, with the exception of one term, 1, the 0th term. We've basically, by multiplying every term by a fourth, we've turned every term into the next term. And since it's infinite, there's no short supply of next terms, right? They go on forever. But there is short supply of the first term. There's only one first term, or is the 0th term really? The 0th term is gone. The 0th term is gone. So we can use that right off the bat. Now we've got a relationship between S, a quarter S, and a fourth, right? The ratio. So there's two ways you can kind of do this. Is that since 1 is missing from a quarter S, we can say a quarter S is equal to S without the 1, or S minus 1. If that's confusing to you, you can do a substitution as well. This infinite tail of S is just a quarter S, right? It's a fourth plus a fourth squared plus a fourth cubed, and so on and so forth. Right? That is 1/4 S. Or S is 1 plus 1/4 S. Now they're the same equation. You see, if you subtract 1 from this equation, you get this equation. Or if you add 1 to both sides on this equation, you get this equation. So they're the same equation. It doesn't matter which one you choose. You'll end up at the same answer in the end. Let's choose this second equation because it's a little simpler. We don't like working with negative signs. They're a little annoying. So S is equal to 1 plus a quarter S. Now what I'm going to do is subtract a quarter S from both sides. And this arrow here, in math speak, means implies, but I'm kind of using it as next, just so you know. And actually, let's make this a little cleaner. Let's do it like this. There we go. So S minus a quarter S is equal to 1. And S minus a quarter S is 3/4 S. There's like a ghost implied 1 here. Or you can factor an S out of 1 and 1/4 and get 3/4. Either way, you get 3/4. S equals 1. Therefore S equals 4/3. There we go. We've gotten to the same conclusion a different way. Instead of drawing squares and splitting them up, we've used an algebraic approach by abusing infinity and this recursion relationship to sort of give us a little head start on what we might want to do. But this is just one case, right? Maybe instead of 1/4, our ratio is 1/3, or maybe it's 2/3, or maybe it's 1 over the square root of 2. Something. There's a general way. There's a general formula for any r. Yay. So, in the spirit of mathematics, let's figure out what that is. Let's call it the formula. The greatest formula of all time. That's a joke, of course. The greatest formula of all time goes to Euler's formula. If you don't know what that is, look it up. It's very cool. Anyway, we're going to do the same sort of things we just did algebraically with the 1/4. But instead of 1/4, we're going to use a placeholder variable for the ratio. We're going to call it r for ratio. So S is 1 plus, instead of 1/4, it's r. And then instead of 1/4 squared, r squared, r cubed, so on. Some of you might be saying, well, why aren't we just using 1 over r instead of r? That makes more sense to me. Well, the best answer I can give you is that using r is just cleaner. It's easier to work with. Working with fractions in general is just kind of messy. It can get really messy really fast. So one reason is that the algebra is easier. In this case, if you used 1 over r, the algebra wouldn't be that much more difficult. Another thing is that the formula that we get in the end is cleaner if you use r instead of 1 over r. And r for ratio, you don't want 1 over ratio. That's kind of a superficial argument, but you kind of get what I mean. And also, we'll get to this later, but there are some constraints on r. R can't take any value, and that also is a lot cleaner as r if you use r here instead of 1 over r. So just trust me, you want to use r. You don't want to use 1 over r. Okay. So we're going to use the same arguments as before. There's a recursion relationship. If you want to get the next term in this series, you just multiply the one that came before it by r. And then there you go. So we say, well, what happens if we multiply every term in the series by r? We're going to get r plus r squared plus r cubed plus r to the 4th plus so on and so forth. And just like before, what happens is that we just take every term in the series and shift it over by one term. And since we have infinitely many terms, again, there's no shortage of next terms. You're shifting an infinite series, whatever that means, into another infinite series. And the only term that you're shifting out of the series, so to say, is the 0th term, this 1 here. So just like before, we're going to do a substitution. This part here is r times s. So s is 1 plus r times s. We're going to subtract rs from both sides. We're going to factor an s out on this side. And then we're going to, sorry, that's a 1 minus r equals 1. And then we're going to divide over the 1 minus r. And there's our answer. For any r, it's just 1 over 1 minus r. I'm betting you that's a whole lot simpler than you thought it would be. It's really not that complicated. And that sort of is a result of the fact that, you know, there's sort of a simple recursion relationship between each of the terms that lends itself to a simple pattern, you know, relatively simple anyway. And some of you might be noticing that some values of r don't work. Some of them are problematic. So let's start. Problematic values of r. R equals 1, right? S equals 1 over 1 minus 1, 1 over 0. Oh no, that's indeterminate. That is a big no-no. You never like to see division by 0. Oh, I spelled indeterminate wrong. Our formula doesn't work, in other words, for r equals 1. And we can kind of see that by writing out s in this case. If r is equal to 1, we get 1 plus 1 times 1 plus 1 times 1 times 1 plus, you know, 1 plus 1, and that goes on forever. So in a way, our formula tells us that it blows up, which is, you know, what we find. In other words, the limit as we add more and more terms approaches infinity. And, you know, as a side note, you can think of the geometric series as kind of a limit. You can think of this, you know, as a limit if you want. I think it's helpful to me. So let's get back down to the last page here. You know, our intuition tells us it blows up. And, you know, you might be wondering why is our formula not working? What's wrong? Well, in deriving this formula, we've kind of assumed that it was going to be finite. We assumed that s is not infinite, right? For a given r, this formula kind of assumes that it doesn't blow up. Which, of course, in this case, you know, everything our intuition tells us says this blows up. This does not converge to anything. Here's another one. R is greater than 1. Some of you might be saying, well, you know, that's not going to blow up, right? The denominator is finite. Well, if r is greater than 1, the denominator is less than 1. It's negative. And if that's true, s is negative. Right? 1 divided by a negative number is a negative number. And that is just bonkers. Because if r is greater than 1, then s, 1 plus r squared plus r cubed, so on and so forth. Our recursion relationship tells us that each successive term is getting bigger, right? Each term is bigger than the last. And they're all positive. And the last, right? So if the case where in no terms, you know, every term is exactly the same, they're not growing or reducing, it blows up, then certainly this blows up too. And everything about our intuition says this blows up as well. Because each term is just getting bigger and bigger and bigger. So how can S be negative and positive? Furthermore, how can it be finite and infinite at the same time? How can it be positive and negative at the same time? How can it be how can it be finite and infinite at the same time? Well, it can't, right? Something, our formula is going against our intuition. Our intuition says that, again, the limit approaches infinity. Our formula says, no, it's negative. It's negative and finite. Well, that there's no way, right? It's impossible. And again, the problem with that is that our assumption is that it's finite. And if r is greater than 1, it's not finite. And so we're getting kind of a hokey answer. We're getting an answer that doesn't work. So r can't be equal to 1, and r can't be greater than 1. In other words, our ratio has to be less than 1, and intuitively that makes sense. Every term has to be smaller than the last. Otherwise, it's never gonna converge to anything, right? So S equals 1 over 1 minus r assumes that r is less than 1. The absolute value of r is less than 1. And that means that, yes, r can be negative. So, for example, r equals minus 1/2. If that's our ratio, what happens is you get alternating signs on your terms. They're getting smaller, but they're kind of flip-flopping around 0 between positive and negative values. And that comes from the fact that you're taking a negative number and squaring it and then cubing it and then to the 4th power, 5th power. Every term that has an even power is going to be positive, and every term that has an odd power is going to be negative. In this case, we'll get 1 plus minus 1/2 plus minus 1/2 squared plus minus 1/2 cubed. Sorry, my camera's in the way there. So S equals 1 minus 1/2 plus 1/2 squared minus 1 over 2 cubed plus, so on and so forth. And we can use our formula. We can, S is equal to 1 over 1 minus r, which is minus 1/2, which is 1 over 1 plus 1/2, which equals 1 over 3/2, which is 2/3. So you can see our formula worked. And even for a half, a half, like I said, it converges. It converges to 1. So why shouldn't minus 1/2 converge to something? In the case where it's 1/2, everything is positive. And geometrically, even if algebraically this isn't convincing, you can geometrically show that the case where it's 1/2 converges to 1. And if you put a 1 in front, it'll be 2. But if it's minus 1/2, every other term is negative, so it should also converge. And in this case, it converges to 2/3 instead, which is pretty cool. And that's really all I have to say about the geometric series. And infinite sums for today. I'd like to thank you all for tuning in. I hope you guys had fun. I hope you learned something. In the wise words of Porky Pig. That's all, folks. See you later.